Okay, so today we start 7.3. 7.2. We should do 2 before we go to 3. The key concept here in this section is that we're going to use a sample proportion. We know that the best estimate from that sample, that gives us the best estimate of the population. We're going to use the sample population to construct what we call a confidence interval. That confidence interval, depending upon what my level of confidence is, will give us a certain percentage of confidence that the mean of or the proportion of the entire population will fall within that interval. And also we'll be able to calculate how big of a sample we need to be able to estimate a population proportion. So some definitions here. A point estimate is a single value or point used to approximate a population parameter. I don't think we've had that little P with a thing over it yet, have we? No? Okay. The sample proportion, that's pronounced P hat, is the best point estimate of the population proportion P. So you want to make sure that P hat and P, you recognize the difference. P hat is the sample proportion, where P is the population proportion. P hat is sample, P is the population. So here's an example. The Pew Research Center conducted a survey of 1,007 adults and found that 85% of them know what Twitter is. The best point estimate of P, and P is what? The population proportion, is the sample proportion P hat, and P hat is 0.85. So a confidence interval is a range. It's an interval where I'm going to say I'm 95% confident that the population proportion will lay between these two numbers. Okay? Confidence level is the probability of 1 minus A, often expressed as the equivalent percentage that something will actually occur. Most common choices for that confidence level are 90, 95, or 99%. Okay? So alpha being 0.1, 0.05, and 0.099. So of course, this is a 90%. This is 95% and a 99%. That's my confidence interval, confidence level, the degree of confidence. So we must be careful of what a confidence interval actually means and be able to state it correctly. So the confidence interval is stated this way. The P, and P is what? The population proportion, is between 0.082 and 0.872. What that actually means is that we are 95% confident that the interval from 0.828 to 872 actually does contain the true value of the population proportion P. We're getting that from our sample, aren't we, from P hat. And then we're setting a level of confidence and finding what that interval will be. It actually means that if we were select many different samples of 107 adults, and we construct the corresponding confidence intervals, 95% of them would contain the value of the actual population proportion. Okay? So we can use it to test some claim, and it will be used again when we do our formal hypothesis testing, when we'll make a formal judgment based upon that hypothesis test. But for now, we're going to learn how to construct them. Critical values. Z-scores are going to be used to distinguish what we are calling critical values. First, to be able to do this, we have to have a sampling distribution that can be a normal distribution, normally distributed. A z-score associated with the sample proportion has to have a probability of theta divided by 2 falling to the right of the tail. So we just studied that, and that was on your test. And I said it's going to become more important again because we would be looking at it. We did, I think I put that problem on the test, or maybe I put 0.05, I forget. You have different numbers on your test. Well, what it's saying is we're going to find z at alpha divided by 2. And again, that's going to be the area to the right of that z. Okay, the right of the z. So if we had a confidence interval of 95%, alpha is 5%, right? So it would be z at 5 divided by 2. And I'd want to find the area. I'd want the z when that area is to the right of z. It's a really bad looking z. It looks like a big fat 3. There we go. Okay? So this is a picture of those critical values. Again, note that z is, oh, sorry, I thought I had a highlighter. Z it as alpha divided by 2, and it's referred to a critical value because it's the borderline separating z-scores from the sample proportions that are likely to occur from those that are unlikely to occur. And we've used those terms before. So the reason we're taking alpha divided by 2 is because we don't want any extreme down here at the bottom, and we don't want any extreme there at the top. So if my, it doesn't say anything here, but if it was 95%, it would mean then that this is 95% here. And of course this would be 5 divided by 2 is 2.5 and 2.5%. So you can see that those are those critical values. 95%, that's our confidence that it's going to be in there. And then here's our tails that we don't want any on either tail, the low tail or the high tail. So again, just to have that definition, critical value is the number that the borderline separates the sample statistics that are likely to occur and unlikely to occur. So here we are having that 95% confidence level. 95% would fall in here. And then I have my two critical values. And it's 0.025 and 0.025 or 2.5% on each tail. Here's a table of the ones we're going to use most often. 90, 95, and 99%. If I were you, I would just keep this chart handy because you're going to use them that much. No, you'll have to remember them, or you can get them from your table, or you can get them from your calculator. So if you don't have that, how would you find that? How would you find your Z? Pretending that this last column isn't here. Pretending your last column isn't here. How would you find the Z for a 90% confidence level? Here's my critical values, right? And I want this to be 90%, right? So what is alpha? 0.10. So that means alpha so I want the Z of alpha divided by 2, right? What is alpha divided by 2? It's what? 0.05, correct? So really what's happening is I have 0.05 here and I have 0.05 there, correct? I'm breaking that 10% up on both tails, dividing it up. So how would I, if I didn't have this given to you, how would I find it? Inverse norm, absolutely. So let's go do that just to show you. That's what we just got our test on, right? Inverse norm. What am I going to put as my area? Okay, if I put 0.05, it's going to give me this Z-score, right? And I'm going to use for mu, I'm going to hit 0. And for standard deviation, sigma is 1. And I get negative 1.6448. It's negative. And it rounds it this way. If 5% is here and Z is negative 1.645, what's Z here? Same thing but positive. Does that make sense? So if I gave you one that's not listed up there, let's do 98%. Let's do 98%. I can get my board to work again. Here we go. If I gave you the confidence level of 98%, you guys do it on your own. We'll come back and check. So I had to find my values for 98%. It means that I'm going to have critical values somewhere here and somewhere here. And in the center is going to be 0.9800, right? How much is going to be on each tail? 0.01. That just makes sense, right? And I'm going to find that by going to my inverse putting my area to be 0.01. And I'm going to find negative 2.3, we'll round that to 3, negative 2.33, and again this would be positive 2.33. Make sense? Excellent. These you'll use a lot because most often we will have 90, 95, and 99% confidence level. So why would I have different confidence levels? That's just a great question. Why? Why do you think we would do different confidence levels?
Show how precise the numbers are.
Okay, to show how precise the numbers are. Wouldn't I want everything to have the higher confidence? Okay. Because sometimes that's going to make my interval a little broader than I want to get 99% in there. But if I am testing a new drug, would I want a high level of confidence? Yeah, so 99% would definitely be what I'd want for something like that. If I was, I don't know, testing how many adults know of Twitter, is that critical? No, so I could probably have a lower confidence level. Okay, does that make sense? Okay. So, we want to talk about this thing called margin of error. And we're going to take a random sample to estimate the population proportion P. Remember, population proportion P. The margin of error is going to be denoted by capital letter E. And it is the maximum likely difference between the observed proportion P hat, which is what? The proportion of the sample, and the true value of the population proportion P. Because it would be almost impossible to do an entire population. But we can certainly do a sample from a population. We're going to use that as the point estimate and then build a confidence interval of what we know percent confidence between those two intervals. And the way we're going to do it is find the margin of error. So that's your, wow, that is your formula for finding the margin of error, just so you know what everything is. So my margin of error is going to be equal to, this is actually my z-score, right? My z-score when alpha divided by 2 is to the right, correct? So that's what we were just talking about, those z-scores. We found at 98%, what was it, 2.33? So I would be plugging in 2.33 if it was a 98%. If it was a 90%, I would be plugging in 1.645. Okay? And then P hat is our sample proportion, which you know. Q hat, anybody, Q hat? 1 minus P hat equals Q hat. You remember? Yeah. So in the one that we just talked about for the Twitter, the sample said 85%. That would be P hat. What's Q hat? 15%. And N is number in the sample. Number in the sample. Yes, it will be on the formula sheet. Is it in the calculator? Yes. There is. It is in the calculator. Honestly, it's just as easy just to calculate it out. It really is. Oh yeah, you'll see how easy it is. It really is. It really is quite simple. Okay.
Sometimes going over the packet trips me up, but once I see like a question, it's kind of
Right. Yes, soon as, I got to get through all this kind of explanation thing, and then we can get to a problem and then do what we've just said. It makes more sense. When you're just introducing it, it probably thinks like, what is she talking about? Okay, so just wanted to make sure you knew what these terms meant, so put them all up there. P, again, population proportion, P hat, sample proportion, N, number of samples. E is the new one, margin of error. And Z of alpha divided by 2, again, is the Z score separating an area of alpha divided by 2 in the right tail. The other alpha divided by 2 is on the left-hand tail, right? Confidence intervals. The sample needs to be a random sample. And the conditions of the binomial are satisfied, that there is a fixed number of trials. The trials are independent. And that 2 categories of outcomes, a yes and a no. Twitter. Do you know Twitter or you don't know Twitter? Okay. There's at least 5 successes and 5 failures. There's at least 5 successes and at least 5 failures. At least 5 people said yes, they know what Twitter is, and at least 5 people said no, they don't know what Twitter is. How would we check that? That particular one had 1,007 adults, and it said 85%. Somebody tell me, 1,007, 85%. How many other people knew? $896? 856. So 15% didn't, and that would be, you can either take 1,007 and subtract 856 or try 141. Is there at least 5 successes and 5 failures? Absolutely. There's 856 yeses and 141 nos. So I can use confidence intervals. Does that make sense? At least 5 yeses, 5 nos. So here's what you're going to do. This is my population proportion. That's what we're trying to find out from our samples. So we're going to calculate our margin of error first. Then we're going to take p hat. P hat is, again, is the sample proportion. We're going to subtract the margin of error. Then on this side, we're going to take p hat and add the margin of error. Okay? Round the confidence interval limits for p to 3 significant digits. 3 significant digits. It's 151. Okay. Whoops. Okay. All right, where are we? Okay. You can put them in 2 different versions. You can say p hat plus or minus the margin of error. And then you can put them in interval notation. Does everybody remember interval notation from algebra? It means it's going to be between this number and this number. Okay? If there was an interval that said point, I'm just making this up, that would mean between 0.751 and 0.789. That would be another way to put state an interval, a confidence interval. Okay. Procedure. Verify that you can use it. Is it a simple random sample? That's the first thing. It only works for part of the time. That's what I'm convinced of. Okay, so first is it and then it still didn't work, even though it told me I had a highlighter. Then you got to check for the conditions of the binomial distribution. And there's at least 5 yeses and nos. Okay? Find your critical values of z of alpha divided by 2. Once you find those, then you're going to calculate your error, margin of error. And then we're going to take p hat minus the margin of error and p hat plus the margin of error. We're going to remember to round to 3 significant digits. Okay, so we go back to that problem about 1,007 randomly selected adults showed that 85% of the respondents know what Twitter is. So n is 1,007, p hat is 0.85. Find the margin of error that corresponds to a 95% confidence level. 95% confidence level. Now we'll go back off of highlighter to a pen. So what am I doing? I can use my table for that. We have them right there on our table, right? What is my z for a 95%? What is the critical value z at? 1.96. 1.96. So z, it really wants to give me a hard time today, doesn't it? Of alpha divided by 2 is 1.96 for that 95% confidence level. So I need to find the margin of error. The margin of error is equal to z of alpha over 2, so that's 1.96, correct? Then I'm going to multiply by p hat. What's p hat? 0.85. Then I multiply by q hat. What's q hat? 0.15. Divide by n. What's n? 1,007. So 1.96 times the square root of 0.85 times 0.15 divided by 1,007. And we get 0.022054. Is that right? Okay. So I've calculated my margin of error. My margin of error is 0.022054. Okay. So now I need to find B, the 95% confidence interval estimate of the population proportion. What am I going to do? I'm going to take 0.85 I'm going to subtract 0.0220054, and I'm going to take 0.85 and add 0.0220054. Just 1 0? Okay. Oh, it changes color whenever it wants to. That's nice, isn't it? Well, very colorful notes. When I subtract it, what do I get? And when I add it, I get 7, 2, 0, 5, 4, right? So I subtracted it, then I added it. So we need to write now our estimate. So I'm going to put, and I'm going to round to 3 digits, correct? So 0.8279 is 0.828. And I'm going to say it's my population proportion, P, not P hat, because I know what P hat is. And 0.872. So my confidence interval is 0.828 is less than P, which is less than 0.872. On your calculator? Okay, so now that we have our confidence interval, that was B. Part C says, based on our results, can we safely conclude that more than 75% of adults know what Twitter is? Absolutely. What was my lowest level? 0.828, okay. So assuming that you are a newspaper reporter, write a brief statement that accurately describes the results and includes all of the relevant information. In other words, you've got to what? Interpret. Interpret. How would I interpret this? We are, what was our confidence level? We are what? 95% confident.
Our population will be between 82.8% and 87.2%.
Yes, will be between 82.8% and 87.2%. We're 95% confident. Okay?
Yeah,
The,
because P hat is the sample. And
right,
the regular P
is the population.
so since the population's in the middle, we're saying
Yes, 95% confident that our population proportion will be between 8.828 and 872. And I think the next slides just go through the whole example, which I did without going to the next slides. Okay? Analyzing the polls, just to be, when you see things, again, you want to make sure a sample that's supplied is a random sample. Can't be like a voluntary response. It can't be that I'm standing out front of the mall and saying, would you like to have another wing to the mall? Something like that. The confidence interval should be provided. They should state to you it's 95% or it's 99% or it's 90%. The sample size should always be provided. What if they only did a sample of 3? They should state N is, or a sample of that many. And except for relatively very rare cases, the quality of the poll results depends on the sampling methods. We already know that. Okay. Don't think that they're ever unreliable. Okay, population size is usually not a factor in determining the reliability of a poll. Suppose we want to collect the sample data in order to estimate some of a population proportion. But how do we know how many people I should sample? It's called sample size. So there is a formula in determining sample size. Notice it really is the same formula we just used for determining the margin of error, and we've just solved for n. So we have the z-score at alpha divided by 2 squared times p hat times q hat, then divided by the margin of error squared. And we can determine what sample size we need to predict the population proportion. Now, sometimes you know what p hat is. Sometimes you don't. So if you do know, you can just fill that in as p hat times q hat. Sometimes you don't know what it is because you haven't sampled the population yet. You haven't run your survey yet. And when that happens, you use this 0.025. Well, why do we use 0.025? Because if we don't know what it is, we're going to guess that p hat is 50% and q hat is 50%. That's where 0.25 is coming from. So you can either remember 0.25 or you can just plug in 0.5 times 0.5, whatever makes sense to you to find those sample sizes. Now, critical. We're not going to use normal rounding for this. Always up to the next larger whole number, because I can't take 0.1 of a person or 0.1 of an airplane seat. If I use normal rounding and I rounded down, let's just say, and of course it's still not working. I found out now that I have to click it there and click it here. Let's say that we did that and we found n was 879.2. Normal rounding says I would round that to 879. But this is the minimum sample size I can use. And if I rounded down, I did not meet my minimum, did I? So you always round up, and it's going to be then 880. I can't forget that this is part of my sample, so I have to go to the next larger whole number. Always round up. Always round up. Okay? Many companies are interested in knowing the percentage of adults who buy clothing online. How many adults do I need to survey in order to be 95% confident that the sample percentage is in error by no more than 3 percentage points. Okay? So what do I'm looking for what? I'm looking for N. I'm looking for N. Correct? I'm looking for N. N says I'm going to take my Z at alpha divide by 2 and square that, correct? Multiply it by P hat times Q hat, out of room, divided by the margin of error squared. That's my formula, right? So at 95% confident, what is Z of alpha divided by 2? We just used it, right? 1 point, do we have it memorized yet? 1.96? So N is going to equal 1.96 squared. That part we know. And it says up here in my problem that I'm going to have an error of no more than 3 percentage points, right? Then part A says use a recent result from the Census Bureau that 66% of adults buy clothing online. So 66% is going to be P hat. What's Q hat then going to be? 0.34. Everybody okay? So now I'm going to multiply by 0.66 and multiply by 0.34. Then I have to divide this by E squared. What's E? E is my margin of error, right? 0.03, because it tells me by no more than 3 percentage points. So I'm going to be 0.03, and then I need to square that. So let's put it in our calculator so that we know we're not making a calculator error. Here's the key. This whole numerator put in parentheses. So I'm going to put a big parenthesis to start. Then I'm going to put 1.96 squared times 0.66 times 0.34. I'm going to close that parenthesis, and I'm going to say divided by 0.03 squared. So my result says 957.8389. What am I going to report as N, the number for my sample size? 958. So sometimes we give you things backwards, you know that. So these are two more formulas that we can find our point estimate if we know my upper confidence level and the lower confidence level. I'm just going to add those two things together and divide by 2, and I'm going to get P hat. That's really just algebra. And then I can find my margin of error if I take my upper limit minus my lower limit, and then divide by 2. That's really nothing more than algebra. Okay? And that's all of section 7.2.